Hello everyone, welcome to Computer Vision 3, Detection, Segmentation and Tracking, or CB3 DST for short. So as you all know, due to the virus situation, we decided to take this lecture fully online. So we will be recording the lecture and releasing the videos once per week so that you can still keep up with a nice schedule. Okay, so let's get started. So first of all, let me start by introducing the team. So myself, I'm Leal-Taixé, I'm a professor here leading the group of Dynamic Vision and Learning, and Dr. Alyosha Osep is going to be helping out. He's a postdoc in my team, so we're going to be the responsible ones for taking you through detection, segmentation, and tracking. So let's see, what is this course about? So it's a course definitely on computer vision, so there's a very strong focus on computer vision. So we're going to cover the topics of object detection, instance and semantic segmentation, and then we'll take all of this knowledge to the temporal domain for multiple object tracking, both in 2D and 3D. Now, what this course is complementary to is other computer vision courses. There's Computer Vision 1 and Computer Vision 2, and I would especially recommend you to take Computer Vision 2, which is related to multiple view geometry, so how to go from the 2D image space to the 3D world coordinates. Now, this course is definitely not an introduction to deep learning, so we have the I2DL, the Introduction to Deep Learning course at TUM, which is offered also this semester. So if you're not familiar with the basic concepts of deep learning, I would recommend you to take that course before taking this one. It's also not a practical project course, so we have the Advanced Deep Learning for Computer Vision also this semester that we're offering. This is a course very much focused on the practical part, so really coding up solutions for a specific computer vision problem. We will be coding up a little bit in this course, but if you want really a full semester-long project that takes out a lot of time, go and take the Advanced Deep Learning for Computer Vision course. And it's also not a theoretical introduction to 3D vision. So I already recommended you to take the Computer Vision 2 course taught by Professor Daniel Kremers. There's also lectures online on YouTube, so you can check the multiple view geometry course. Now, okay, let me just briefly motivate you for this course, right? So what is computer vision? So it turns out computer vision was a problem first defined in the 60s. So it's quite well, some might call it a new problem, but it's actually has been around for quite some years. And the whole idea was to tackle the problem of mimicking the human visual system. So this seemed quite an easy task for the artificial intelligence group back in the 60s. And they were supposing that this human visual system was supposed to be the center block of robotic intelligence. So we can imagine a robot navigating around an environment. It needs to actually have a pair of eyes that understands the environment, looks around, and understands what is happening around that environment. So this was defined actually in 1966, right, as a summer vision project, right? So something quick to be developed and to be solved in a summer, 3 months. So essentially in one summer, they wanted to construct a significant part of the visual system, essentially solve computer vision in one summer. And at the time, this was very much related to what we call pattern recognition, right? So they thought that the human visual system, what it does is it has a certain set of patterns. And what it does is basically learn, detect, and redetect these patterns. And again, this was proposed in 1966, right, as a 3-month project. And here we are in 2020, still working on it. So not such an easy project, not such an easy problem as they made it sound. So in computer vision, we want to give eyes to a computer, right? So we want to look at the world through a camera and actually try to understand every pixel of that camera, every pixel that is provided by that camera. So every pixel of the image, right? This matrix of numbers, this image, is the only thing we have to interpret the world around us. And so we want to interpret, for example, this world in a semantic way. So know where the car is depicted in the image. So which pixels belong to a car, which pixels are representing a car, or a tree, or a person, or the road. So this is the task that we call semantic segmentation, and we will cover in one lecture how can we actually approach this task with deep learning. Of course, there are certain categories like cars or person where it might not be enough to actually say all of these pixels belong to the class person, but we actually want to identify the different instances of this class. And this is the task called instance-based segmentation, which we will also cover in the lecture. And finally, of course, the world is not static. The world is moving. So we don't really want to understand every pixel of an image, but we want to understand every pixel of a video. And hence, we also inherently want to solve the problem of multiple object tracking. So actually detecting these objects, understanding where they are in the image, and following them over time. So this is overall kind of covered in the task of dynamic scene understanding. So this is very important, of course, for tasks like autonomous driving, right? So a car that is driving around needs to understand the scene around it. For example, here in this demo, there are all these objects that are being detected with bounding boxes. So there are traffic signs, people, cars, and these are detected at each image, but also tracked through time. So you see that these bounding boxes actually track these objects through time. Of course, you can have like more fine-grained representation where each pixel actually is labeled with one semantic category. Now, to understand an image, we will go step by step, right? So at Introduction to Deep Learning, we already saw the task of image classification. So you get this image of the cute cat here on the left, and you want to classify the whole image. So there is, for example, a cat in this image, or there is a dog, or there is a table. Now, one step further is actually to localize this object, right? So we don't want to say the whole image represents a cat, but we actually want to place a nice tight bounding box around the object. So we want to classify the object and localize it. If you do this for multiple objects, suddenly you're targeting object detection, which is one of the tasks that we're going to talk about first. And again, a more fine-grained representation can be the instance segmentation problem. So this instance segmentation problem has been quite targeted in the research community. So you have, for example, here some results of what the community can do as of 2017. So these are the results of MaskRCNN, famous method that we will also cover in the lecture. And you can see that there's a broad range of categories ranging from person, umbrella, skateboard, all the way to donuts. And you can actually detect a bunch of categories in a really precise way and put a mask around them. And so what we can actually do is we can do things like this, which are actually pretty impressive, where we detect a lot of objects. There are a lot of occlusions, a lot of overlap, but we still detect a lot of objects and we put a mask around them in a pretty reliable way. So again, if we actually take this to the autonomous driving scenario, we see that autonomous cars can already see, I have to say, in nice lighting conditions, can already see and understand quite a lot of the environment. So we will cover in the lecture different representations depending on the granularity. So I have already gone over the coarse representation detections and this precise representation, which is in the form of segmentation or masks. And we will also cover giving semantic meaning to these segmentation masks with or without instances. So separating the different persons, for example, from the category people or not. And all of these tasks, all of these different levels of granularity really go well with deep learning, which is why most of the techniques presented in this course are going to be based on machine learning and on deep learning in particular. So then we will take it one step further. We will go from image to video. And of course, adding the temporal domain brings us several advantages, right? So there's a lot of redundancy. Not much is changing from one frame to the other. And we can also use the smoothness assumption. So we can actually use the assumption that things do not change or move much from one frame to the other. So a pedestrian is not going to jump around and suddenly be on the other side of the image. So this is an assumption that we use quite a lot in multiple object tracking. So while this temporal domain has quite some advantages, it also has disadvantages. So usually we have a video at 30 frames per second, which means that you have to do all of your computations, all of your detection, segmentation, 30 frames per second. So it takes quite a while. It's quite computationally intensive to actually process a video. And of course, there's all types of occlusions happening. Multiple objects are moving, multiple objects are interacting. So there's a lot of space to actually do research on to actually fully understand a video with all these occlusions and all these objects moving around. So back in 2009, this dataset was proposed for the task of multiple object tracking. So you see that this is quite a simple dataset. Few objects of interest are moving around. There was this pole in the middle that was an occlusion, so this makes things difficult. But nowadays, what we're doing is targeting more these scenarios. So scenarios where the camera is moving, viewpoints are changing all the way from ground level to this kind of level higher up. There's tons of objects that you want to follow, and even these type of scenarios where it's just absolutely crazy that there's lots of occlusions. All the objects look the same. We're actually trying to track all these pedestrians at the same time. This is a really, really challenging task. So we want to understand where every object is going. We want to also understand how they're interacting and trying to predict the future trajectories, right? This is super important for autonomous driving. And at the same time, we want to get detection, segmentation, semantic results which are consistent in the temporal domain. So this is something that we'll also talk about. So the rough schedule, the rough content of the lecture is going to be, aside from this introductory lecture, it's going to be 2 lectures on object detection, 1 stage, 2 stage. Then we're going to move to single and multiple object tracking, also for 2 lectures. We're going to have a lecture on trajectory prediction. Generative adversarial networks are going to be presented also. Then we will move towards mask representation, so segmentation problems, semantic segmentation, instance segmentation, and video object segmentation. And finally, as a last step, we're going to go towards the 3D world and see how tracking and segmentation is done there. So we will cover famous architectures that you have all probably heard about. FastRCNN, YOLO, RetinaNet. We're going to cover person re-identification through SEMIS network, quite a lot of graph neural networks in the form of message passing networks, and also generative adversarial networks for trajectory prediction, and finally move to the mask segmentation domain with mask-RCNN, OSVOS, introducing also techniques like deformable convolutions, and finally go to the 3D domain. So if you want to know why we're offering this lecture, please visit our web for the Dynamic Vision and Learning Group. So we do a lot of research on all of these topics. So if you're interested, go there and take a look at what kind of research we're doing. So about the lecture, this is going to be a series of 10, 11 lectures covering all the topics that we have talked about. Usually the lecture should have happened on Wednesday from 4 to 6, but due to the virus, we're taking all the course online. So we will record all of the lectures. We will make them available online for you to look at your own pace. So every Wednesday we will release a new set, a new lecture, new video. So please stay tuned on Moodle. So aside from all the information which you can find on the website of the lecture, please also follow Moodle. The exam, we still don't know what the date of the exam, but I can already tell you that there will be a retake exam because this course is going to be permanently moved to the summer semester and only offered in the summer semester. And there's also going to be a practical part, which I haven't talked about yet. And this practical part, successfully completing this part, will give you a bonus of 0.3. So the practical part is going to be a fun internal Kaggle type of competition. So we will have a reduced data set for you to work on, and we'll have a tracking challenge, multiple object tracking challenge. We will give you a code as a starting point. You will all start from the same code, and after that you will have an open competition. So we have made a special video for this practical part to explain you what are the rules of the competition, what kind of things you can, you cannot do. So please go check out that video after this lecture. And as I said before, we will have Moodle as a platform for communication. This is especially important for this semester since there's not going to be any on-site lectures for now. We will keep you updated on the situation. So all common information will be shared there. Please make sure to register. You can ask all kinds of questions online. So for each lecture that we upload, we will open up a forum for questions for that particular lecture. So don't be shy, ask away, and we will try to answer as soon as possible. And as for the Kaggle competition, please make sure to not post solutions there. So it is a competition. So try not to post, full lines of code there, because then everyone else would actually copy your solution. This is not something that you want. So all the slides will be also provided on the website and on Moodle. Any questions regarding the syllabus, the exercise, the contents of the lecture, please use Moodle. If you have any other questions, we have set this email address, dst@dvl.in.um.de. So any questions, please address them there because we will not be answering emails that are sent to our individual addresses. That's all. Welcome to CV3 DST lecture. I'm really happy that you're taking this lecture. We're going to have tons of fun. So stay tuned for the first lecture on object detection.